4.5 is exponential and logarithmic equations. First, we'll start off with the property of logarithms. It says if x, y, and a are all greater than 0 and a not equal to 1, then the following holds. X equals y is equivalent to the log base a of x equals the log base a of y. And since this is an equivalence, we can also say that the log base a of x equals log base a of y is equivalent to x equals y. That's exactly what we're going to be doing in this section, is using this property both forward and backward to be able to solve exponential and logarithmic equations. So first we'll start off with solving exponential equations. We're going to use one of the following methods. We'll either change to logarithmic form, take logs on each side, or equate the bases. As you do your homework, you're going to start recognizing which method is going to be the easiest to use. Solve. Give both exact answers and solutions to the nearest thousandth when the answer is irrational. First example is 5 to the x equals 13. We cannot solve this in its current form, so what we can do is change it to logarithmic form. So we have a log. The base is 5 because the base in exponential form is 5 of 13 equals x. Remember that a log is an exponent, so whatever the exponent is in exponential form, you put it on the other side of the equal sign from the log because a log is an exponent. Now we have this form we can use. You can either use your change of base formula or use the log base function in your calculator. So I'm going to use the change of base formula. Give us some extra practice with using that. So this is my exact answer, is the log base 5 of 13. And my approximate answer is going to be x is approximately 1.594. And here I have 2 to the x plus 3 equals 5 to the 2x. And since I have two exponential expressions, I'm not going to be able to solve it this way as easily. So what I will do here is take logs on both sides. So we're using the log as an operator, taking the log on both sides. What that allows us to do is use that property with the power property where the exponent on the argument comes down in front and becomes the coefficient of the log. So I have x plus 3 all times the log of 2. And here I have the 2x times the log of 5. Now the way that helps is that now x is not in the exponent, and we can just solve this algebraically from this point on. First I want to distribute, so I have x log 2 plus 3 log 2 equals 2x log 5. And then I'm going to get my x's on the same side, so I have 3 log 2 equals 2x log 5 minus my x log 2. And now that I have my x's on the same side, I factor out that x to get it away from the other things that are with it. And now I can divide by 2 log 5 minus log 2. So x is 3 log 2 over 2 log 5 minus log 2. Now this is all in base 10, so we can easily use the calculator. But this is our exact answer. We've solved for x, and we haven't touched the calculator yet. Now we'll get an approximation. We have 3 log 2 divided by, make sure that you put your denominator in parentheses since it's a binomial, 2 log 5 minus log 2, closing each of those arguments, and then close the parentheses for your denominator, and we get about 0.823 is our approximate solution. So be prepared to give both the exact and approximate solutions on these. Here I have e to the x to the 4th equals 1,000. Anytime you have an e in the problem, that means you're going to want to take the natural log instead of a log, the common log or any other base. So we can go ahead and change this exponential form into natural log form. So we have natural log base e of 1,000 equals x to the 4th. So e to the x to the 4th equals 1,000. So now to solve for x, I'm going to take the 4th root. So the 4th root of that, and I get x equals, don't forget your plus minus, x equals plus or minus the 4th root of the natural log of 1,000, and that's our exact answer. And then we'll get the approximate answer is x is approximately, grab the calculator, we have the natural log of 1,000 there, and you can take that to the 1/4 power, and so we get approximately plus or minus 1.621. On this next problem, you have a little bit of tidying up to do. We do have common bases of e, but we have to get these together on the left side. First, when you multiply numbers of the same base, you add the exponents. So this becomes e to the 2x plus 1, which equals 2e. Now I can divide both sides by e, and that way I'll have only e on the one side. When you divide numbers of the same base, you subtract the exponents. This has an exponent of 1, so it'd be e to the 2x plus 1 minus 1, or just e to the 2x. Alright, now that I have the exponential expression isolated, then I am going to change it to natural log form. Again, because it has an e, you're going to use the natural log. Natural log base e of 2 equals 2x. Then we're going to divide both sides by 2, and x is the natural log of 2 divided by 2. That is your exact answer. And getting an approximate answer, we go to the calculator, natural log of 2 divided by 2, and we get about 0.347. On this problem, I can see that it's going to be no solution because I have some number to an exponent equals a negative number. There is no exponent you could put on a positive number that would turn it into a negative number. If you didn't recognize that right off, you can go ahead and try to solve with changing it to log form, say. So we say if we have the log base 1/9 of -9 equals x, we know already we can't solve. We can't have a negative argument. Okay, so we'll just say that that can't be negative there. So there is no solution. And even if you want to try this into your calculator, you can do that. Let's try the log base button. So math up to log base, and we have 1/9 and -9. So if you still didn't recognize at this point that you can't do that problem, go ahead and put it in, a non-real answer. Example 6 here, I need to isolate the exponential expression. Now, so you recognize what the exponential expression is. It is simply the 1.4 to the x. It does not involve this -4 here. It does not involve this 3. This 3 does not have the exponent on it. So we need to isolate that 1.4 to the x just by algebraic means. So we have 3 times 1.4 to the x equals 64. Then we'll divide both sides by 3. That gives me a 1.4 to the x equals 64 thirds. And now I can change to log form. I'm going to have log base 1.4 of 64 thirds equals x, and use your calculator to figure that. Log of 64 thirds, and divide that by the log of 1.4, just using the change of base formula, and I get, this is my exact answer, and my approximate answer is 9.095 to the thousandths place. All right, example 7 looks very different, but it is an example of a problem that is quadratic in form. You see, we have this e to the x, and this is really an e to the x squared right there. So we have this problem that is quadratic in form. We can go ahead and just factor. So e to the x times e to the x gives me my e to the x squared. I'm going to have two negatives, a 5 and a 3, exponential. And I have e to the x equals 5, e to the x equals 3. Then I'm going to come up here and change to natural log form. The natural log of 5 equals x. The natural log of 3 equals x. Again, those are the exact answers. And to get our approximate answers, we simply put it into the calculator. X is approximately 1.609, and natural log of 3 is approximately 1.099. Those are approximate to the thousandths place. All right, and this is another problem very similar to this. This is 3 to the x squared, so you can rewrite it as such. 3 to the x squared minus 12 times 3 to the x plus 35 equals 0. We're going to try and factor this, so might as well get everything on one side equal to 0 at this step. And factoring, I get 3 to the x and 3 to the x, and with my 35 being positive and that 12 being negative, I know I have two negatives, 7 and a 5, and now I have 3 to the x equals 7 and 3 to the x equals 5, and changing that to log form, I'm going to have log base 3 of 7 equals x and log base 3 of 5 equals x. At that point you have your exact answers, and we'll put this into the calculator. Log of 7 divided by the log of 3, and I have x is approximately 1.771, and log of 5 divided by the log of 3, I get x being about 1.465. Again, those are approximate to the thousandths place. All right, our next set of problems are the logarithmic equations that we need to solve, and we'll use one of these methods. We'll change to exponential form or equate arguments. Now there is a caution here. Just like when we get logs, we have an additional domain restriction. We have to check our solutions when we're finished to make sure that the solutions we come up with are allowed. We cannot have arguments that are negative or 0. So whatever answer we come up for, an argument, we need to make sure it's not negative and not 0. Give both exact form and approximations to 3 decimal places when necessary. We're going to solve these. So we're going to isolate the logarithmic expression, similar to isolating the exponential expression. So first task is to get natural log of x by itself. We do that just by algebra, dividing by 3. So the natural log of x equals 3. And then we change to our exponential form. We have e cubed equals x. This is our exact answer. And using our calculator, we can get e to the 3 is about 20.086 to 3 decimal places. For this one, we have a common log, so the base is 10, and we already have the first step done for us. The log expression is isolated, so we can go ahead and change to exponential form, and there we are. To isolate the x, we can just say x is equal to 3 minus 10 to the 0.75. This is, again, this is our exact answer. And putting this into the calculator to get an approximation, 3 minus 10 to the 0.75, we get a negative 2.623. Here again we have log base 7, and the log is isolated, so we're going to go ahead and change to our exponential form. So 7 to the 0 is x cubed plus 65. Now 7 to the 0 is 1. 1 minus the 65 is a negative 64. That is our x cubed. And if we take the cube root of 64, you can see here math, taking the cube root of 64, you'll get 4. So that would be a negative 4 as a cube root of a negative. So x is negative 4. Now the deal here is that's the only answer we're going to have. We don't have an approximate like we did on the previous 2 problems. It's just the exact answer. Don't let that bother you. On example 4, we have 2 logarithmic expressions and equals 1. Well, we've always said that we need to isolate the log. Isolate the log. The log means we have 1 log, but we have 2 logs in this equation. So how would we get those logs to be 1 log? We use our properties of logs and combine those logs. When you have 2 logs of the same base being added, then you can write it as a single log and multiply the arguments. Okay. Now that we have a single log isolated, then we can change to exponential form. This is a common log, so the base is 10. 10 to the 1 is 2x squared plus x. So 2x squared plus x minus 10 equals 0. And we're going to try and factor this. And I get x is a negative 5 halves, or x equals 2. Now remember, we have those domain restrictions, so we need to check our solutions back into our original equation. Here I have an x. If x was negative 5 halves, then this would be an undefined log, so we can't use that. If x is 2, this is fine. 2 times 2 is 4 plus 1 is 5. That's fine. So we end up with just one solution, and we don't have to have an approximate. Again, this is very similar to the one we had before. There is another method. We could go ahead and combine the logs by writing a single log and dividing the arguments, or I can simply rearrange this. So I have log of 3x plus 5 equals the log of 2x plus 4. Now, if you refer back to the property that we started this lesson off with, if you have two logs of the same base that are equal, then it follows that the arguments are equal. So we have two logs here that are equal to each other, the same base. The only way that can be true is if the arguments are equal. So we go ahead and set the arguments equal to each other and solve using algebra. And we do still have to check. When I put an x of negative 1 in here, this is a negative 3 plus 5 is 2, and that's fine. And a negative 1 here, that's a negative 2 plus 4 is 2. So it doesn't make either one of those arguments negative, so that is our answer. Don't forget to check these. Number 6, we have 3 logarithmic expressions, but we could put these two expressions together, and then we would have the log equals a log and be able to equate the arguments. So this is actually quite easy. I have the natural log of 15. I have a negative 3x and a negative 5x is negative 8x plus x squared equals natural log of 50 minus 6x. All right, now that I have the natural log equals the natural log, I know the only way that can be true is if my arguments are equal to each other. So then I have an equation of x squared minus 2x minus 35 equals 0. And I'm going to continue to solve that over here. X minus 7 and x plus 5 equals 0. So I have two proposed solutions, and I need to check to make sure that they will work. For the x equals 7, if I put a 7 in here, it makes this 3 minus 7, which is negative 4. I can't have a negative argument, so I have to throw that out. If I use a negative 5, then that makes this a 3 plus 5, which is positive. 5 minus negative 5 makes 10, and that's positive. 50 minus negative 30, that's positive, so that is fine. Notice my positive answer did not work, so I had to throw it out, but my negative answer did work. It's not whether it's positive or negative numbers, it's what it does to the argument. If it makes an argument negative or 0, then you have to throw it out. All right, this is very similar to the one before. We have log base 2 of 5x minus 6 over x plus 1. We're subtracting logs, so we can write as a single log and divide the arguments. This is equal to log base 2 of 3. Now we have two logs equal to each other of the same base, so the arguments must be equal. And then I get a 5x minus 6 equals 3x plus 3 by multiplying both sides by x plus 1. And that gives me 2x equals 9, and x is 9 halves. Again, you have to check 5 times 9 halves. If you are concerned about that, you can use your calculator. 5 times 9 halves. That's going to be 22.5 minus 6 is positive, and of course 9 halves plus 1 is positive, so there's no problem with our proposed solution. We'll go ahead and circle that. This problem, we can go ahead and combine the logs on the left side. So it'd be a natural log of e to the x over e cubed, which is equal to the natural log of e cubed. Again, we have a log equals a log, so the arguments must be equal. And I'm going to solve, just get rid of the fraction. If I multiply both sides by e cubed, then I get e to the x equals e to the 6th. And then I can equate my bases, just like when we solved exponentials. E to the x equals e to the 6th, so x must equal 6. And we can see that that's going to work there. It doesn't do anything wrong with the argument. It doesn't make the argument negative or 0, so that is our answer. We have a couple of interest problems here. We have $5,000 invested in an account at 4% annual interest that's compounded continuously. So how much will be in the account in 8 years if no money is withdrawn? What we need to identify here is what kind of interest. This is compounded continuously. So this is going to be the amount at time t is equal to p e to the rt. So that's our compounded continuously interest formula. We have $5,000 that's invested. E to the rate is 0.04 as a decimal, and the time is 8 years. And we want to know the amount in 8 years if no money is withdrawn. So this is quite easy. We just put it into the calculator, and 5,000 times e to the 0.04 times 8, and I'm going to get $6,885.64, rounding appropriately to the nearest cent. Now the next problem, we're to find t to the nearest hundredth of a year if $1,786 becomes $2,063 at 2.6% interest, with the interest compounded monthly. Now compounded monthly is a different formula from before. That's going to be a of t equals p times 1 plus r over n to the nt. So our principal was $1,786, and the amount at whatever time t, which is what we'll be solving for, was $2,063. 1 plus our interest rate as a decimal is 0.026. The number of times it's compounded per year is 12. It's compounded monthly. To the n, that's the same n as this n, times t. Our job is to solve for t. So one thing that we'll do is go ahead and divide both sides by 17.86. So I have 2,063 divided by 1,786, and this is going to be a 1 plus 0.026 divided by 12 is, we'll put this, record it on the paper as this, but when you use it for further calculations, make sure you're using that number in the calculator. Okay, so now we have the exponential expression isolated. We can go ahead and change to our logarithmic form. So I have the log of 2063 over 1786, and leave room for my base. My base is the 1.002167, and that is going to equal 12t. But to get my t by itself, I need to divide by 12. So t is the log base 1.002167. Just make sure that you're using that number that's in the calculator that we just found. And so t is approximately, they want the nearest hundredth of a year. So I'm going to have the log of this number that we had here is going to be my base. So we've got 2063 divided by 1786, and we're dividing that by the log of this number there. And if you want, you can go ahead and hit enter and then divide that by the 12. So we get 5.55 years, rounded to the nearest hundredth of a year. The next problem, we're trying to find an interest rate. At what interest rate to the nearest hundredth of a percent will $16,000 grow to $20,000 if invested for 7.25 years, and the interest is compounded quarterly? So again, compounded quarterly means we're going to use this formula. A of t equals p times 1 plus r over n to the nt. And we fill in what we know. We have $16,000, and we want it to grow to $20,000. And 1 plus, we don't know what the rate is, so that's going to be our variable to solve for. And it's compounded quarterly, so that means 4 times a year, to the 4 times 7.25 is the number of years. And let's see what we can do to solve this. We've got 20,000 divided by 16,000, so it's going to be 5/4 equals 1 plus r over 4 to the 4 times 7.25 is 29. Okay, and what can we do here? We're going to take the 29th root of both sides. So the 29th root of 5/4 equals 1 plus r over 4. We need to subtract 1 and multiply by 4. So the 29th root of 5/4, then we'll subtract 1, and that's equal to r over 4. We're going to multiply by 4. So 4 times the 29th root of 5/4 minus 1 is our interest rate. So let's put this all in there. 4 times parentheses, we'll go math down to the xth root, and it should give you a template. We put in there 5/4. Get out of the radical and subtract your 1, close your parentheses, and hit enter, and we get an interest rate of 0.030897. If we want to round this to the nearest hundredth of a percent, it's going to be 3.09. So 3.09% is our interest rate on that. That does it for this lesson. Go ahead and try your homework. Let me know if you have any questions.